Thanks. Yeah. Let me thank Manas and Abhishek and other organizers for getting us all together here and inviting me for the talk. So this is the work I'm going to talk about. It's the recent work we have been doing. Very simple model calculations, and we'll try to convince you, just like last two speakers, that Lindblad equation doesn't work. Okay? So we all agree on that. I'm from, of course, this inaugurating a physical chemistry department, so I can't do without showing you molecules. Okay, so this is another reason to show it. The reason is that there was some discussion last, second week of there was a talk, and somebody asked whether it's possible to observe these normal modes of the molecule in junctions. And here is one example. So this is an experimental work. This is the molecule, which is a long name, I can't read it. It's coupled to two gold leads through these sulfur atoms, and then they observe the current through this system, and of course it shows you the symmetry because the molecule has this symmetry of left and right. And what happens actually, if you look at not just the current, but the first derivative of the current, you observe, or second derivative to enhance these oscillations, you observe these nice oscillations in the current. So it's quite nonlinear through this molecule. And the reason these oscillations are there is because these electrons, which are tunneling through this molecule, are interacting with the vibrations of the molecule. So it's an interaction, it's an energy exchange between this electron and the vibration of the molecule, which show up in this so-called di by dv is a conductance. Yes. This is the experiment, yes. So these are different vibrational modes of the molecule. And so this allows you to do some kind of spectroscopy. So this is called inelastic electron tunneling spectroscopy, IETS, I think. And it's very useful to identify the configuration of the molecule, the way it is coupled between two leads, or it could be on the metal surface. So it can tell you how these molecule is sitting on top of the metal surface by looking at the vibrational modes of the molecule. So this is one kind of spectroscopy. In general, these interactions between electron and molecular vibrations lead to the enhancement in the current, because it leads to a new channel for electron to go from this side to this side. Okay. This is one way to explore this vibrational motion of the molecule in molecular junction. There is another way where you can actually, these people have done some experiment again, where they, together with the current, they observe the optical response of the molecule. So this is the Raman signal, and this is the molecule sitting in between two gold leads. And then as this junction is formed, you see that there is a time dependent. The time is meaning that this junction is formed as a function of time. So they use some technique to actually so-called electron migration technique to make these single molecular junctions. And so when this single molecular junction is formed, they observe the current through this system, and at the same time they shine light to enhance certain vibrational modes. These are the vibrational modes that they can enhance, or these are the ones which are actually absorbing most of the light. So when these modes are excited, at the same time they see that the conduction is also going up. So di by dv, this is the conduction, this is the optical response. So there is a nice correlation between the molecular vibration and the conductivity of this molecular junction. Same way they see this same pattern for this molecule. It is a bit more complicated, but you can identify that there is some kind of positive correlation for these modes of the molecules of vibration with the conductivity of this molecule. Okay? They also noted that there are certain modes which you can enhance, then the conductivity goes down. So it's negatively correlated with your conductivity. It's a very nice way. And then they, of course, propose that this can be used for optical switches. So with optical lights, you can enhance or you can excite these vibrations to turn off and turn on the conductivity of this molecular junction. We have actually done some work in this direction, not exactly this, but looking at the optical response of this, not this particular molecule, but benzene coupled between two leads. And if you're interested, you can look in these papers. This one is just the frequency resolved. So you look at the frequency signals. Here, this time resolved, which gives you time-dependent information. Okay, so that's it about the molecules. Really, I'll not go into the calculation or show any more results about this molecule. This is the, yes. No, so for real molecules, we do real calculations, so quantum chemistry calculation. Time-dependent density function theory, yes. Because you need all the excited states of the molecule also, right? This is an experiment which is very clean and I really like it. You have two quantum dots, left, right, which are, so there is a coupled to a battery and the current is flowing through this. There is another circuit which is directly coupled to these two, capacitively coupled, for example, asymmetrically coupled to this left and right dots, and this is the tunneling junction. So there is no quantum dot, there is a tunneling junction. And by monitoring this current in this junction, in this circuit, they could tell whether the electron is sitting here or here. Okay, so if the electron is sitting here, it affects the current differently than when it is sitting here. So by looking at the fluctuations of this circuit, which looks like this, they could tell whether the electron is here or it has jumped to this side. And in this experiment, they actually studied the statistics of the two jumps, consecutive jumps from left to right. So there is a time delay between these two jumps, and you see there is a broad distribution of these times. And so these kinds of things can be done. So fluctuations can be studied at the single electron level. And theoretically, one can analyze these fluctuations in the particle transfer between left, right. And if you look at the net number of particles transferred from one side of the circuit to the other side, this distribution shows some nice symmetries, which are known as fluctuation theorems, which are very general these days for any non-equilibrium system. And these ratios are generally related to this exponential quantity. N is the number of particles transferred during this time t from left to right. And beta is the inverse temperature, V is the applied bias. In general, these ratios are related to the entropy production in the system during the observation time. And in this case, N beta EV is nothing but N number of particles transferred from left to right with this bias energy EV. And this looks like, this is actually the entropy flow from the left lead to the right lead, or left side to the right side of the circuit. So this is nothing but the entropy flow, which can fluctuate because N is a fluctuating quantity. But on an average, using some methods, of course, Vijay also talked about this a little bit. So this actually leads to the conclusion that on an average, this entropy production is always greater than equals to 0. So fluctuation theorem, this is at the microscopic level, which couples to the macroscopic thermodynamics. And it serves as a very nice link between the two regimes. Yeah. No. So if you count once, so it's like, okay. So infinity means t is large compared to the relaxation time. So what I'm doing is that I have this system, I couple it to the leads, I call it at time t is equals to 0 some time. Then so I already counted the number of particles this side. Yeah, so this n is actually not, so I'm not doing the statistics of this t here. But I'm saying that it's possible to do the statistics of the particle transfer from left to right in experiments. That should involve the projective. So in the steady state, what you can think of is the statistics between this is going to be the same as statistics between this. So I can do the statistics of particles going between these two. Right? So what I'm saying is that if you measure on this dot, then it turns out that theoretically because the dot is only 0 or 1, the fluctuations are 0 in the long time. So it's better to do statistics on this side because you can have large number of particles over a time t going from this side to this side. So there's no bound on the fluctuations. So does it answer your question? Okay, okay. Right, so I will talk about a little bit about this also related to the work we have done. So these were the three different experiments, and there are different theoretical methods, of course. Standard methods are quantum master equation, which is based on density matrix. There is something also called scattering method, which is wave function dependent because it's amplitude. And then, of course, non-equilibrium green function method, which in principle is exact for most of the cases, as long as I can treat my bath non-interacting. As Abhishek also mentioned about quantum Lagrangian equation, I think the Bindu and Dipti Mansen, they are using it extensively, and Takis and Ashish also talked about this similar technique in quantum optics, I mean, right? But I just realized after Abhishek's talk, I've written it in light because I was not sure what it was. But after your talk, it became more clear. It looks like what you are doing is actually done by some people in scattering method also recently. So they also look at this amplitude and trace out, the interactions. But again, at the second order. Right, so let me move on. So what I'll do is that I'll focus on this and this technique only. I'll not talk about these two. So let's just look at this simplest case when I have single level or single quantum dot with one level where electron can come, coupled to two leads. And these are the coupling gamma L and gamma R, the strengths of the coupling or the rates. It determines the rates. And then I have two chemical potentials. Temperatures are same in this case. Very simple example. If you do master equation, this is now, in this case, there are no, of course, coherences. So Lindblad is same as Redfield. And what you observe is that the current is given by this formula where FL and FR are the Fermi functions of the left and right. And if you do a green function calculation, you can still do it analytically. And this complicated looking, the result is from the green function method, okay? What you can show is these are the so-called digamma functions related to gamma function derivatives. And these are well known. So this is our analytical function. All symmetry properties of these functions and expansions are all known. What you can show if this beta gamma, beta is the inverse temperature, gamma is actually sum of these two left and right. If this goes to 0 or it becomes much smaller than 1/2, this result is exactly same as this result. So you can show it analytically. So it shows that the master equation result is valid in the limit when beta gamma is going to 0. Okay? Right. So now, okay, I have something complicated looking. So the next question is, how does it compare? I just look at the IV characteristic of this junction. So blue one is my quantum master equation result. This red one is my complicated looking expression. I really don't see much of a difference. Qualitatively, both are the same. And this is the result when coupling strength is 0.5 and epsilon is 0.5, beta is 1. So temperature is 1, is big temperature. If I increase the coupling, I still don't see much of a difference. Both are saturating to almost the same value. Saturation, of course, the times, the behavior is slightly different, but qualitatively it is still the same. This one is exact calculation, right? Yes. A green function method, right? So, yeah, I mean, I still see that this is qualitatively same. So it tells you that what's the advantage really. But as I said, it's valid only in the beta gamma equal to 0 limit. But here I took gamma quite large, still it's qualitatively same. So next thing is we try to do the gamma as a function of gamma. How does the current look like? And here, of course, you see that the master equation result simply varies linearly in gamma, while this other method gives you a saturation in the current. You expect a saturation because as the gamma is increased, your transmission probability or the channel is conducting, in a more efficient way. So when the coupling is very strong, there is hardly any backscattering. The electron is able to pass through. So it saturates to, for a given value of voltage, it will saturate, but it will change with bias. So this is what we understand. So the question we ask is, look, I know that this is different qualitatively, but is there any physics that we are missing? Is there any physics that you can say, okay, quantum master equation, like Abhishek said, if you look at the bond current, I will also discuss that a little bit, then quantum master equation doesn't give you any bond current, I mean Lindblad equation, right? So that is inconsistent because there is a current in the system, so it should be flowing between the dots. So I will give you some examples, these three examples basically. One is the quasi-adiabatic charge pump, which is nothing but an effect of the Berry phase in the system. And then I will talk about something called local currents, which is a bond current, nothing but the bond current. And then I'll talk about some what happens when a molecule is strongly coupled. It's not really related to the comparison between quantum master equation. In some sense it is, but okay. This is some surprising result we found, and I thought I should discuss with you. It's not published still, it's in archive. Yeah, this is what I'll show you. No, where? Here? No, so first, okay, I'll tell you that. Yeah, that's my last part of my slide. Yeah, in this case, it will not go down at all. It's a single level system, but I'll show you it goes down because of the coherences in the system, not, yeah, double quantum dot case. I remember that if I do the red field, for double quantum dot, again, it depends how you couple it, I mean, serially or parallel. It gives you this behavior decay, but the decay is not correct. I mean, it gives you non-monotones, right? Yes. So it's precisely because of coherences in the system, because red field has some coherences. Okay, right. So let's look at, so what is this quasi-adiabatic modulation that I'm talking about? We all know that when a state of a quantum system is taken around in a loop in a parameter space, the state develops a phase. Okay, that phase is generally called the Berry phase because Michael Berry was the first one who predicted this. And this has to be done adiabatically, only in the adiabatic limit or quasi-adiabatically. In that limit, your state develops a phase as you bring it back to the same state by changing the parameters. Yes, you have a question. I know. Okay. That's fine. Yeah, we are good friends, right? So what happens here? In this case, you take this Hamiltonian and you vary two parameters or more parameters. You at least need two parameters to vary, and these should be independent. Your state, when you come back after some time period t, it develops a phase, and you can show that this phase has usual dynamic contribution, which comes because your eigen energies are changing in time, and you have to integrate it over. This is the usual one, but there is some part of it which is called the geometric phase, and it is connected to this area that you trace in the parameter space in going this circle. So this area is directly proportional to this Berry phase. So that is why it is actually called the geometric phase also, because there is a connection with the geometry in the system. So what I'm going to talk about, the effect of this geometry phase. How does it show up in this open quantum system? Michael Berry, of course, showed it for the closed quantum system, and we know that for closed systems, it leads to different kinds of effects. Like, for example, current in a ring, when then you have magnetic field passing through the ring. I'll talk about that also a little bit. So let me just show you an experimental result where they actually showed the effect of this Berry phase. This is a 2D gas, blue one. And then these are the electrodes. By trapping these electrons between these electrodes, which are negatively biased, you can, I think Jason talked about it a lot. You can create this quantum dot here. And these are the source and drain. So these are two-dimensional electron gas between this semiconductor surface. And then there are two extra electrodes where the voltage is varied in a cyclic fashion. And as you vary these voltages, there is a phase difference between these voltages, okay? So what they observed that initially there is no applied bias. If you change this voltage with a phase difference in a cyclic manner, there is a voltage developed across this. So there is a current flowing, starts to flow between the source and drain. Okay, and they show that this phi, as you change the phase difference, at phi is equals to pi, there is no voltage developed, but otherwise there is a voltage developed across source and drain. And they have some flux, magnetic flux also. So these results are for different magnetic flux that is applied to this quantum dot. But I'll not talk about this magnetic flux. So in my calculation, there is no magnetic flux. The question was that in this case, what they observe, they say that these electrodes actually couple the source and the dot, while these electrodes are only changing potential inside the quantum dot. Okay, so they attribute this effect to some kind of coherent. So what you're doing, they claim that you're changing the phase or changing the wave function of the electron at these two ends of the quantum dot, and that coherent effect is actually giving rise to this. And they explicitly mentioned this, that they don't change the coupling. So these voltages do not affect the coupling between the source and the quantum dot. So we naturally ask, okay, what will happen if you really change the couplings, right? Instead of this, do you see the similar effect or it will be different effect? So we were thinking about this, and then the same time we found a paper by Hengi. He showed actually in 2010 that the Berry phase, but in his case it was a thermal bath coupled with this two-level system. And he showed that indeed by changing the temperature of these two baths in a cyclic manner, using this rate equation, you could show that there is a net heat which transfers between these two, even though there is no temperature gradient. Okay, it can transfer heat between left and right. And that is precisely because of Berry phase. I'll show you how it comes, but that's the effect of the Berry phase. But then he mentions that if you change the couplings, okay, if you change the couplings, that's what we were thinking to do. What happens that because couplings do not affect the detail balance, it doesn't break the detail balance, and as a consequence of that, there is no flux. Okay, so we were a bit disappointed. The student was very enthusiastic about this. He said, no, we should go ahead and let's do it. So he started doing this. So this is the model. I vary the coupling, left and right couplings with some time dependence, periodic driving. And well, this is the Hamiltonian. It's not really. So you just set up the master equation for this system. There are some technical problems because this equation is valid, not this one. Master equation is valid only for small coupling, and then you change the right. So gamma is the square, modulus square of these quantities T, which is the coupling, right? That's why I said it's proportional to gamma. Rates is proportional to gamma. It's not. So these rates, gammas are proportional to this mod square of this coupling. Sorry, this gamma. Oh, it's purely decay. It's pure. No, it's a decay. It leads to decay. Right. So I do usual trick in the master equation. These are simply rates. Okay, these are simply rates. Yeah, clear. So we can set up this master equation, and then what you can do is that you go. This is a formal solution of this master equation. In this case, my Liouvillean is time dependent because the rates are changing in time, and then you can do. You can go to the eigenbasis of this Liouvillean to solve this, and this is the result for that. What happens that you can show that there are two terms in the exponential which are arriving. This is, you can connect to the so-called, what I mentioned, dynamical part. So this is purely because of the eigenvalues of this Liouvillean operator. And this is something related to this matrix U, which diagonalizes L. So it's like the basis transformation of the basis with time. And these are the matrices which are making this transformation. And gamma is simply this diagonal matrix. Now, in general, what you can show is that because you're changing it over time, if I need to integrate this quantity over time, because this time dependence is coming explicitly from outside as a change in the parameter, you can write this time integral as an integral over those parameter values. Okay, so this is a transformation from time to parameter. It's just simply like what you do in the uh, path integral methods, where you have time and you go to the trajectory level, right? So it's simply like that. Then using this, the Gauss theorem, you can couple it to. So these are the parameters: lambda 1, lambda 2. It can be it's a vector, and this is another. This quantity is defined here. So this is now dependent on the parameter instead of time, and then this integral is over this contour that I have in the parameter space. You can go to the surface integral here, from here to here, and this quantity is called so A is the Berry phase which develops. This quantity is the curvature of this Berry phase, and the way I have written it, it looks like A is some kind of vector potential in this case, and this curve of this vector potential gives rise to some kind of magnetic field. You can think of this. So this magnetic field is of course giving rise to some Berry phase in the system. So in this case, when you do it using the master equation, you can show that this quantity A turns out to be 0. It doesn't exist at all. And this is what Henke was saying, that there is no Berry phase. If you can change the couplings, gamma L, gamma R. So in some cases, it can happen that the A is finite, but its curvature is still 0. So A is there, but doesn't lead to any magnetic field. But in this case, this A itself becomes 0. So there is no Berry phase effect if you change the gamma L, gamma R. And this is what the prediction from the master equation. Okay. Now I'm going to show you something very quickly. In this case, there is no heat or charge pump. These details are here because I'm not focusing on this. So we wanted to formulate this problem in terms of green function now. Okay. We said, okay, there are several approximations in this quantum master equation. Let's go beyond this. And then, of course, you know the green function. Several people have talked about it. These are the Keldysh green functions. T is the time ordering on the Keldysh loop. And then, of course, in the real time, you can show that there are, depending on the time ordering, you have retarded and advanced green functions. But if there is no time ordering, then these correspond to some correlation function of the system, which we call lesser and greater green functions. But basically, this is showing you the particle propagation. You create a particle, you destroy it later on. This is called the particle green function. In some sense, it's related to the population of the particle. And this is the whole, the reverse sense. Okay. These green functions have well-defined Dyson equations. In this case, sigma is the self-energy coming entirely because of the interaction with the bath, which is very simple. And one can calculate the current in the usual method, and you can show that this current turns out to be in this form where it depends on this lesser and greater green functions. These are the self-energies from the bath. Lesser or greater simply means that they depend on the lesser green function and greater green function of the bath. So these are the green functions of the system, and these are the, you can call it green function of the bath. Okay, but this bath is at equilibrium, so I know these quantities. Only thing is to calculate this. Now, okay, that's all right. Now I'm changing the parameters, okay, with time. So what is happening is, I need to separate these two time scales. So there are, these correlation functions are changing in time. One is because of the Hamiltonian dynamics. The other one is because I'm changing parameters by hand. And I assume that these parameters changing very slowly as compared to the Hamiltonian dynamics in the system. But I still need to separate these two time scales. And so so gamma is the parameter which determines the Hamiltonian time scale, and TP is the time period of my driving, and I assume that this is much longer than inverse of this gamma. So how do we separate these two? And it's a standard trick of Wigner transformation. I go from this TT prime times to something called capital T in tau, which is basically nothing but the relative times and the center of mass time in some sense. So you can think of this, this gives me the, if I have several particles, this gives me the motion of the center of mass of this particle. This gives me the relative motion of different particles, which is of course going to be fast compared to this. And that's how you can actually separate out these two time scales, slow and fast. There are some technical things. So after doing this separation, this is a fast time scale. I'm not much interested in that, so I will just Fourier transform this, which is omega in this fashion. This is standard. And if there is a convolution of two functions like sigma g in the Dyson equation, it will transform like this. So it leads to some kind of exponential derivatives in between these two Wigner transform functions. So what I will do is that once I have done this, because I know that my variation with t is very small, I will expand this exponential and keep the leading order term. Okay? So that way I can just basically doing the perturbation in the external perturbation. And I will just look at the leading order term. If I do that, what I can show is that in the Wigner space now, these are the Fourier transform, Wigner transform of the green functions. This is a matrix, by the way. It is lesser, greater, and all those components are there. So it's a 2 by 2 matrix in this Keldysh space. And you can write down to this leading order, this is how the Dyson equation should look like. Okay? And the next step is, of course, so the adiabatic term is simply this quantity here. So I know this G naught, this is the initial green function. Self energy is known in this case, it is non-interacting. So we just calculate this green function and we calculate the current. Here I'm not showing the current, I'm showing the number of particles that you can transfer per unit cycle of this variation. It gives you something very nice analytical result where f is now something called tri-gamma function. Okay, these are all known functions. So what we observe in this is that if the two drivings are identical, of course, you cannot transfer any number of particles. Okay, so this was known because you have to have some phase difference between these two drivings. So once it is satisfied, next step that I'm going to show is another surprising result was that if I am in resonant with the chemical potential of the lead, remember the chemical potentials are same of the two leads. There is no applied bias. So if the chemical potential is in resonance with the energy of this quantum dot, then of course the imaginary part of this function is 0, and then also the number of particles you can transfer is also 0. So there are two conditions to meet, of course. One is that gamma L, the rate of change of these couplings should be different. And the next is that it should not be in resonance with your chemical potential. This came as a surprise. Okay, so the point is that using green function, you can actually show that it does lead to some kind of flux in the system. And this is what we show, just a plot of the, for this kind of driving. This we call even driving, because if I change this whole thing by minus, it remains same. So this is just a definition that we gave. This is the even driving. So here what we show is that identical to what they see in the experiment. So it's not obvious whether what they say is that it's a coherent phenomena because the wave function is changing, but we believe that it could be because it's affecting the left-right couplings as they change these bias inside the dot. Okay, okay, fine. So now with this, we went ahead and we did some statistics of this particle that you're transferring from left to right, and we could calculate the full distribution function for these statistics. And what we show here is that this logarithm of this Pn minus 1 is a straight line because P ratio is exponential. It should go linear in n. So fluctuation theorem is also satisfied. What Hangi said doesn't hold here, that the fluctuation theorem in his case doesn't satisfy. In this case, we showed that it remains valid. There is no problem with the fluctuation theorem. Now for this kind of driving, what I call symmetric driving, what we found that these fluctuations of n, number of particles that you transfer, only odd fluctuations are affected by this Berry phase. Even fluctuations are not affected. Okay, so current is of course an odd average, and that's why you have current, because it is due to the geometric contribution. Okay, in this particular case, I have this is for when I have 100 times done this cycling. This is the result for that time. Okay, okay, this I'll close now. So okay, let's not go close this. So this result that when mu is equals to in resonance with my dot energy, there is no current. When I have off resonant with this chemical potential, then I have some current. Came as a surprise, and we thought this could be related to the fact that quantum master equation doesn't give you any current in the system, because what is happening is actually when you are resonant, let's think about temperature 0 case, for example, all these states are not occupied. This is the broadening of my level. Okay, this is the broadening due to the bath coupling. So all these states are not occupied, these states are occupied. So I have nice symmetry between electrons and holes. And as I start changing this coupling, this quantity, it should be actually a Lorentzian. It just broadens and squeezes. So this symmetry remains intact. I don't change the number of particles in the system or number of particles in the hole. But if I'm off resonant, then as I change the broadening or squeeze it, the number of particles in the system changes. So what you see is that this is what we show here. This is the change in the number of particles on the system as I change the coupling with time. And this black line is the one when they are in resonance. The chemical potential is resonant with this. So there is no change in the population on the dot. So we believe that it is the effect coming because of the broadening induced by the bath, which is not there in the quantum master equation. And that's why this effect is not seen there. We are not 100% sure, but this is what we believe. This is the effect of broadening. In some sense, it's the effect of, we can say, non-Markovian in the system, non-Markovian. So, okay, this is it. Let me just go quickly to this bond current calculation that we did at the same time when Abhishek was also looking at it. So this is the system. This is a ring coupled to two leads. Symmetrically coupled, our coupling strength is same. I have magnetic field. And then I'm interested in knowing what is the bond current between, let's say, 1 and 2. Okay, and you can calculate between 4 and 1 also. This is again coupled to my Green function. This is the operator. I need to average it. In terms of Green function, I can write these quantities. Phi is the flux that is passing through this ring-like structure. Okay, what we could show that this bond current between 1 and 2 actually has two components. One is due to this applied magnetic field. Other one is due to applied bias. And we could identify these two components here. What we observe is that, okay, IV is an odd function of phi, even function of phi and odd function of the applied bias. Just the reverse holds true for this field-driven current between 1 and 2. So obviously we were interested in actually knowing whether you can control these bond currents. Okay, so the one thing is that you can calculate this bond current, the other one is how to control these bond currents. There is a huge interest in this molecular electronics community to identify different conducting channels within the molecule so that you can connect it more efficiently to the leads. So in this case, we wanted to know that. So for phi is equals to pi, of course, both these contributions are 0. I'll come back to that if it is possible. So we were interested. Yeah, of course, yes. It doesn't lead to any net current in the system from left to right. It's just transport, yeah, between 1 and 2, or in the ring, right? But it allows you to control this bond current now. So because these have different parities with respect to phi and voltage, what I can do is that I can change the direction of phi, right? Make it negative and change the parameters so that it flows opposite to IV. And that way you can cancel the bond current between 2 and 1. Right? So you can selectively, and same thing you can do between 4 and 1 here. 4 and 1. So you can selectively cancel this current or this current. But this kind of thing is quite trivial because this is you are changing the phi in the direction and making it negative. But what we found numerically is that actually you don't need to change the phi direction. So the blue curve is the values of bias and applied magnetic field, where the 1-2 current is 0. So the white region is the one where both the branches are conducting. Okay, 1 to 2 and 1 to 4. But blue one is the one where only one of them is conducting. Red one is conducting, and on the red one it is the blue one is the 1 to 2 is conducting. Here 1 to 4 is conducting. Okay, so you can tune your bias in the magnetic field such that only one of the branch conducts the current, the other one doesn't conduct. Okay. What is interesting here to note is that this current, which is the phi contribution or the field contribution, comes entirely because of the populations of the system in the eigenbasis. Okay, so if eigenbasis has some population, it only contributes to this I phi, and well, you can show that it is zero because these populations or these eigenstates. So in this case, eigenstate 1 and eigenstate 4 are conducting this current, but in opposite direction. That's why you have negative sign. And you can, if you tune this phi, these eigenstates become degenerate at different points. And because of this degeneracy, this current contribution can become zero. It happens at phi is equals to pi. For example, here, phi is equals to pi. 1 and 3 are degenerate. Here, 2 and 4 are degenerate. So this cancels out. Same thing happens at phi is equals to 2 pi. Okay, so contribution of I phi is zero because of the degeneracy in the system at certain points. And if you do the calculation, because populations contribute only to the I phi contribution, as you connect these eigenstates to lead, of course, leads are going to mix these eigenstates, creating coherences, and all those coherences contribution are in IV, the other contribution to the bond current. And when you transform these coherences to the local basis, you can show that these are nothing but the interference between these two pathways. So I'm just talking about IV now, the voltage-driven current. This current has contribution only because of these coherences or interference between 1 and 3. So these two pathways at phi is equals to 0, IV also becomes 0 because we can show, it's a bit complicated, that these two pathways interfere destructively, and that leads to IV current. So I phi is 0 because of the degeneracy, and IV is 0 at phi is equals to pi because these two pathways interfere destructively. Now, okay, this is the punchline. Lindblad quantum master equation gives you IV is equals to 0 because it doesn't have coherences, right? IV has all the contributions from the coherences. It doesn't have any contribution. So IV must be 0. And you can't have this selective cancellation of bond currents within the master equation. It will still give you a bond current if phi is if the magnetic field is non-zero. But if the magnetic field is 0, then it will not give you any bond current because IV is strictly 0 there. This is what shown here by these people. I'll quickly summarize this last part. It will hardly take 3-4 minutes. I just consider this simple geometry. I have two dots coupled like this. I can change these couplings. I call it a serially coupled case when L1 and R2 are 0. L1 and R2 are 0. So this is the coupling. It's a serial coupled. And the other one is side coupled. When it is coupled like this, this one is hanging. It's not coupled to anything. So these two cases I will consider. I can do exact calculation again within the green function. And what do I see? The current as a function of the strength of the coupling. Again, the coupling is same, left and right, I'm assuming. And when this is serially coupled case, when it is coupled like this, okay, both this one is coupled to this one is coupled to this is the current. And as I keep on increasing the strength of this coupling, current actually goes to 0, which is very unexpected because my system is coupled strongly to the system. It should lead to increase in current or at least saturation, as I discussed earlier. In the other case, it actually saturates. It doesn't go to 0 in the side coupled case. So we were just curious to know how it happens. This is not published, actually, it's still in archive. And so we went back to eigenbasis analysis and the Lindblad will simply give you a straight line. For both, actually. It simply gives you straight line. Not Redfield, Lindblad I'm talking about. Yes. Yeah, completely fails to give anything. red fill, for this particular case, I know, this one I don't know, and I have seen it in some paper, I have not derived it. It gives you something similar, but it decays so here decay we could show is 1 by gamma square decay, but red fill gives you 1 by gamma. That's very slow decay. Blue, no, I have not done red fill for blue. It saturates, but I don't know red fill result really. Okay. So in the eigenbasis, if you go to eigenbasis in case of serially coupled, you have of course plus minus states, something we call bonding, anti-bonding orbitals, molecular orbitals, and you can show that they look, in this expression, they look exactly like this single level. They are not coupled at different energies, and they are conducting independently. So these eigenstates conducting independently, and there is a coherence induced by these leads between these two eigenstates, which you can calculate like this. It's a bit complicated to do it in finite temperature. For zero temperature case, you can show actually the eigenbasis currents are this, and for large gamma, this actually saturates, but the coherence actually for large gamma gives you this part 0. So coherence is exactly negative times of the sum of the contributions from the two eigenstates, and that's why it actually gives you negative current, which is exactly equal to the sum of the currents contributed by these eigenstates. And that's why it is, that's how it is making it 0. And this is the numerical result where this is the coherence. So contribution of the coherence to the current. These are the contributions from the eigenstates. Both are identical in this case. Parameters we have chosen such that both are the same. This is the net current. Okay. Well, in the other case, in the side coupled case, you can do the same analysis. Here also you can see that the coherence, the current carried by these coherences is again negative for large gamma. And the populations always contribute positive current. In this case, these two are not cancelled exactly. They vary linearly, and then so net current is actually saturating. What is the message here is actually is that the eigenbases always contribute positive current, and coherences always contribute negative current, at least in the large gamma limit. Okay, and this result, what I have shown you, analytical result is done within wideband approximation, but we did some numerical calculation where we introduced some spectral density of the bath. The numbers are different, but this qualitative behavior remains the same. I think with this I'm done. Most of the work on the quantum master equation is done by Himanshu. He's a postdoc now in Dresden. Hari has done all this green function calculation. He's sitting here in the crowd right now. And I thank ISC for funding and other facilities. Thank you.
Urgent question. We said them all.
So you at some point you showed that that exact thing has would be same as sort of Lindblad if some beta gamma is small and
right. Let me. It's yeah, first few slides. Then I know.
Yeah. So my question is, so that basically means that at zero temperature these things will not work.
It's tricky. So if I take beta going to infinity, you're saying, then this term can never be smaller than 1, right? Yes, so I guess if you take beta going to infinity, then there is no point taking gamma going to 0. So it's basically beta gamma has to go to 0, small. But what you can do is that if you take gamma going to 0 first for a finite beta, and then take beta going to or temperature going to 0, then you can recover this. Of course, in that case, it is simply theta functions, right? But yeah, I mean, beta gamma has to go together to 0 in this case, right?
Okay, we better move on to the next talk. Let's thank our speaker. Thank you.